Hello, and welcome to a lecture on Directivity of Apertures. My name is Steve Ellingson. First, an overview of this lecture. I'll remind you about the concept of directivity. Then I'll remind you about the three different methods that we already have available for computing directivity. Then, the main topic of this lecture is a derivation of a fourth method, which is particularly useful for apertures. And I mean apertures of all kinds: phased arrays, reflectors, horns, and so on. And then we'll see that there's a connection between this new method and the aperture efficiency concept. Okay, the directivity concept. The definition of directivity is maximum power density relative to average power density. Now, this is a transmit mode concept. This is the context in which we introduced it, and it is really the most fundamental definition of directivity. But as you no doubt realize, we can also talk about the directivity of a receive system. So that's accomplished by relating the concept of effective aperture through reciprocity. So when we did that, that allowed us to define a directivity in the receive case. And in that sense, the receive directivity is equal to the transmit directivity. Of course, directivity is also related to gain through radiation efficiency, and we're not going to really address that here. That's a relatively simple concept, and I'd like to separate it from the current discussion just to keep things simple. Also, no doubt you recall that directivity can also be used as a pattern metric. In other words, we don't have to think of directivity as being the maximum directivity over the pattern angles. Now, we're not really interested in the pattern application of directivity. More often, we use normalized field patterns or normalized power patterns for that purpose. Okay, method one. Method one, we just apply the definition. Right? The definition of directivity is the maximum power density over the average power density. And of course, one way we can get that is we can find the maximum power density, and we can get this average power density by computing the total power, which has been applied to a lossless antenna, and divide it into 4 pi, and this is a typo here, it should be r squared, 4 pi r squared, right? Because that will also give us the average power density, right? Total power divided by the area at some distance r should give us the average power density at that distance. Now, to get the total power, what we do is we take the power density and we integrate it over some sphere, and of course that sphere is at a radius r. And to get the power density that we need for that integral, what we do is we apply the Poynting vector. This is a Poynting vector, E cross H conjugate, take the real part, divide by 1/2. This is assuming, of course, peak units. So that's a lot of work. We have to first find E and H, then we have to integrate the Poynting vector over that, and then we also have to do this business. So that's quite a bit of work. Method two, we can do this from the normalized pattern via the beam solid angle. And there the idea was first compute the normalized pattern, then compute the beam solid angle, so that's just an integral over the normalized pattern, and then finally compute the directivity as 4 pi over the beam solid angle. Now, that's also a lot of work. After all, there's still a two-dimensional integral involved. But this is probably more convenient if you already have pattern data. So in a lot of engineering applications, we have pattern data for antennas because we've measured them in a range or something of that nature. And so this turns out to be a more convenient way to do it in that case. We don't have to go all the way back to the fields. Now, back in a lecture on large rectangular apertures with uniform excitation, we found that the directivity to a good approximation could be described as 4 pi over lambda squared times the dimensions of that rectangular aperture. And of course, this is just the area of the aperture, the the product of the side lengths is the area of the aperture. And this worked if you had relatively large directivity. That's what the approximation is about. And it's specific to uniform excitation, of course. Now, in this concept, we notice that this is, of course, related to the relationship between effective aperture and directivity in the received case. So you can go ahead and make that connection that this must therefore be the effective aperture in this problem. And we're finding that the effective aperture is approximately equal to the physical aperture when we have uniform excitation. Now, the new method that we're going to talk about here, method 4, will turn out to be essentially this, but now we're going to have it for any shape, and it's going to be a somewhat more general expression. So let's go ahead and work this out. So method 4, the derivation. We start off with the expression for directivity in terms of beam solid angle, 4 pi over beam solid angle. Then recall that beam solid angle is given by total power over maximum radiation intensity. That's from a previous lecture. And if we make that substitution, then we get this expression that directivity is 4 pi times maximum radiation intensity divided by total power. Now, maximum radiation intensity, which we need in this expression, is given by the power density in whatever direction it's maximum times r squared, the distance to that point where we're actually doing, or that surface where we're doing the calculation. Now, this direction of maximum power density for a uniformly excited aperture in the xy plane, that's theta equals 0. So in other words, there's no loss of generality in doing this, but just to establish some coordinate system to think about the problem. We're talking about an aperture here which lies in the xy plane, and then angles relative to broadside are theta. So in the direction which the directivity is greatest, that's along the z-axis, or theta equals 0. The power density in that direction, well, if we know the fields, the electric field intensity, then we can compute the electric field intensity in that direction, take magnitude squared, and divide by 2 times the free space impedance. That's a simple plane wave relationship, which again applies because we're in the far field. We're assuming we're in the far field here. And that we can compute, this expression we can compute using one of our aperture expressions, one of our expressions for the field radiated by an aperture. Now, remember, there are a whole bunch of expressions that we have. This, in fact, is one of the type 2 F expressions, and it assumes transverse electromagnetic backlighting of the aperture. So this assumes that the aperture is being illuminated by a plane wave which is normal to the aperture. In other words, something that looks like this. It's not a plane wave coming in from some oblique angle. It's a plane wave coming in directly. And that's the way we're modeling the aperture. Now, it doesn't actually have to be a backlit aperture. In fact, it's not. This was the free space aperture expression. But this turns out to be a convenient one to use, and it applies to a whole bunch of problems, including phased arrays and reflector antennas. So this is the one we would like to use here. Okay? So if we use that expression, we can compute the power density in that direction. There's a little bit of math here that I'm skipping, but it's relatively straightforward. You should certainly make sure that you know how to do this. But when you do this calculation, you find that you get wave number squared, 8 eta, pi squared, r squared, and then the spatial Fourier transforms of the aperture electric field enter into the expression in this way. So px conjugate plus py conjugate. Now, this thing in the brackets we can write in a slightly different way. You recognize that this is equal to px magnitude squared plus py magnitude squared. And of course, that's just the magnitude of the spatial Fourier transform integral of magnitude squared. So we can go ahead and substitute that expression for the spatial Fourier transform. This you can look up from one of the previous lectures. And we get this. So magnitude squared of this integral. Here are the aperture fields. So we need to know the aperture fields, and then you have this phase factor which appears inside the integral. Now, that part, the phase factor, in this case is going to be very, very close to 1. And the reason is because we assumed that the direction of interest is theta equals 0. Let me show you why this is. So here's R. That's pointing to the field point, which is along the theta equals 0 direction. Here's the aperture, and here are values of R prime, right? Because R prime are all points in the aperture. So we see that everywhere in the aperture, R prime is perpendicular to R hat. So since these two things are perpendicular, the dot product is 0, and therefore this exponential phase factor is equal to 1. Okay, so now we make that substitution. We get the same leading factor multiplied by the magnitude of the spatial Fourier transform, which has been simplified using this realization that we have here. And so the maximum radiation intensity, again, from this expression, is simply what we just computed times r squared. So it's the same thing again with no factor of r squared. Okay, now we have to compute the total power. Here is the general expression for total power. Now that's normally an integral over a sphere in the far field, right? The way we've been talking about doing this before is we have some antenna, right? And then we put a sphere out here in the far field, right? And that's the thing we integrate over. That's the surface S that we integrate over. But in fact, this expression works if we have S be any aperture through which all the power must flow, because we're making a power measurement here. So if the surface of integration is any surface over which all the power flows, then it works. So there's no reason to go out here and use some surface that's bounding the antenna. What we could do is have S just to be the aperture, because all the power must flow through the aperture, so the integral will work if we do that. So let's do it that way. Here we're identifying that the region of integration is the aperture. Here's our expression for the power density. It's just the aperture field magnitude squared divided by 2 eta. And the beautiful thing here is we know what the aperture fields are. dx and then dy, because we're integrating over the aperture. 1 over 2 eta is a constant, so that comes out. And we're left with this simpler form. 1 over 2 eta integral over the aperture of the magnitude of the aperture field squared. And then we substitute these expressions back into the directivity expression. So 4 pi times the maximum radiation intensity, derived on the previous slide, divided by power, which is what we've just computed here. And we get this expression here. 4 pi over lambda squared, right? From the maximum radiation intensity, we get this magnitude of the simplified spatial Fourier transform. And then from the total power, we get this integral of the magnitude of the aperture field squared. So everything is in terms of the aperture fields. This is the expression that we're interested in using. This is method 4. So here I've written the resulting equation, right? This is typically the fastest way to get the directivity of an aperture, because you don't ever have to go to equivalent currents. You don't ever have to compute the radiated fields, right? You can get the directivity directly from the aperture fields, right? And if you can make a good assumption about what the aperture fields are, that's great. But however, beware, this is approximate. There's a number of approximations that have gone into this derivation. So if you're required to have high accuracy, you should be careful to evaluate the effect of the approximations. So let's just try this for a case where we know it should work. The uniform aperture distribution. What happens? Well, here we get this. We get this. This is simple to compute because this is a constant over the aperture. That constant can have a value E naught. That E naught factors out of the integral, and then what we see is E naught squared times the magnitude of just an integral over an aperture. Right? On the bottom, we have a very similar looking situation, except the order of taking magnitude squared and integration are reversed. So here we still get E naught squared coming out of the integral, because it's a constant with respect to all of this, and then just this integral over the aperture. Of course, this is the area of the aperture. Right? And so is this. So what we have here is magnitude of the area of the aperture squared over the aperture, area of the aperture, right? Which is simply just the area of the aperture. So we find that the directivity is 4 pi over lambda squared times the area of the aperture. That's an expression that we've seen before. Right? So the value in having done this now is we see that the effective aperture is equal to the physical aperture under these approximations. And now we've obtained it for any aperture shape, because when we did this, we did not assume it's a rectangular aperture. We let that be completely general. Here's the definition of the aperture here appearing in the integral. So this works for any aperture shape. In fact, I'll tell you one other thing that's convenient about this expression, and that's that it's relatively simple to adapt to other cases, such as when the directivity is not broadside. Now you can think about how you might go about doing that. You have to redo part of the derivation, but the idea is still simple. You end up with an expression which is in terms of aperture fields. But in a case where the beam is off broadside, it's just a different set of aperture fields. So this is a quite useful expression and quite simple to adapt to other situations. This concludes this lecture on directivity of apertures.